Hi everyone, and in this session we're going to cover the basics of how to code deep networks from scratch in PyTorch. So by the end of this session you should be comfortable with the basic PyTorch syntax, recognizing that it is based in Python and so manipulating PyTorch tensors is very similar to working with NumPy. We will demonstrate basic tensor operations and introduce the modular coding structure of PyTorch networks, including how to define layers and activation functions, and in parallel we'll discuss how PyTorch implements backpropagation through automatic differentiation through the construction of computation graphs. From there, we'll talk about how you pass your data through construction of dataset classes, which read and process data before passing samples to data loaders for batching, shuffling, and parallelization. In the second video, we will learn how to set up network classes and implement training and validation loops. To follow the examples in these slides, please download and run the code in the Python notebooks, which can be done most simply using a Google Colab environment. For instructions on how to use Google Colab, please see our slides on coding environments. So why do we recommend that you code with PyTorch and not other AI coding frameworks such as TensorFlow or Keras? So in our opinion, PyTorch strikes an ideal balance between offering a simple and intuitive coding framework whilst allowing sufficient flexibility to allow users to design their own solutions without abstracting away the underlying logic within high-level network functions as traditionally offered by Keras. Crucially, PyTorch implements dynamic computation graphs, allowing code to be run and debugged line by line in an interpreted fashion just like regular Python. Combined, these features have made it the global standard for rapid prototyping and academic development, with the vast majority of research papers now using it over TensorFlow. TensorFlow, by contrast, has pivoted towards offering performance and deployment advantages for enterprise-grade solutions, with particular advantages for low memory devices. It's historically been less useful for teaching and research, as its basic usage became moderated through front-end use of Keras, which allows users to deploy entire networks but with less flexibility to design their own solutions, a bit like scikit-learn's offerings for classic machine learning. And finally, JAX is worth being aware of. It's an increasingly relevant solution for advanced numerical computing. So rather than a full-service deep learning framework, it's a functional programming library that excels at running complex math extremely fast on GPUs and TPUs. And for this reason, it has become a foundation for a new generation of efficient AI libraries such as Flax and Equinox, which are used to train the world's largest foundation models in scientific simulations. Nevertheless, functional programming requires an entirely different way of thinking, which we consider too advanced for entry-level deep learning courses. So, let's demonstrate the utility of PyTorch by first looking at some basic syntax for creating a data object, specifically a random array of size 2 by 2 by 2, where this example is given in your tutorial notebook. You can hopefully see for yourself that the syntax is very similar between NumPy, the popular Python matrix library, which we will import as np to then call np.random.rand. And for PyTorch, which we're going to import as torch, we're then going to call our array as using torch.rand. Now note, since you are generating random arrays, we are not expecting you to see the same output when you run these lines of code. Now looking at indexing, we can see that NumPy and torch arrays are indexed in exactly the same way, and that reshaping is very similar, both using a function called reshape, and that conversion of to and from PyTorch tensors to NumPy arrays is pretty straightforward. So for example here, we define a NumPy array A, and then to convert this to torch, we use the function torch.from_NumPy and pass it the array A, and out of that we get a torch tensor that we call A_torch. Then to get back a NumPy array, we can convert back to NumPy just applying the function .numpy on the torch tensor directly. So we've got A_torch.numpy, open bracket, close bracket. And this then converts this torch tensor back to a NumPy array that we call A_np. Here, I'm showing an example of type conversion. So in this case, changing the tensor type to double using A_torch.to and then passing it the argument type torch.double. Finally, Torch offers another option for flattening tensors using view. So here, the -1 tells it to infer the length of this dimension from the total size of the array. So in other words, if we pass the function view the arguments 1 minus 1, then this is going to stretch out the tensor into a row vector with length equal to the total number of elements in the original array, which in this case is 9, or 3 times 3. Now pause the video and run these lines of code in your notebook to check that you're comfortable with them. So let's now look at how PyTorch implements computation graphs. So here I'm showing a visual depiction of a computational graph that I created for our lecture on implementing neural networks from scratch. In PyTorch, these computation graphs are encoded dynamically, meaning that they are reset from scratch at each iteration through the forward pass to give maximum flexibility during training and allow you to debug as you go. So the nodes of those graphs store the forward and backwards operations needed to inform the automatic differentiation. So for example, take the simple operation for multiplication of two tensors. The construction of the dynamic computational graph for this operation will look a bit like this, shown on the right here. All implemented automatically using PyTorch's AutoGrad class. The graph itself traces backwards from the outputs to the inputs, such that the leaves of the graph are the input tensors and the roots of the graph are the output tensors, or the result of the final operation, where in this case we only have one operation. So the gradients are being traced from the roots to the leaves using the chain rule. So all this is made possible because PyTorch tensors don't just store the data, they also store a range of attributes that allow them to remember whether they are a leaf node, i.e. is leaf, and whether they need to track gradients, requires grad, and if they do, whether they need to keep a record of the size of the gradient, .grad, or gradient functions, .grad underscore function, in order to support this backpropagation operation. So this, for a simple example of multiplication, x, y, and z here are tensors, represented in green boxes. And z results from the multiplication of x and y. So the operation, the multiplication, is represented by a purple box. In this operation, x and y are leaf tensors because they represent the start of the operation and therefore the end of the backward operation. Whereas z cannot be a leaf as it's the result of an operation. And in this case, because we only have one operation, it's a root. So taking this one step forward, we're going to imagine now that we want to backpropagate only the gradient of z with respect to x. So that means that we set requires grad equals true for x. Note that this requires grad attribute is therefore telling PyTorch AutoGrad whether it should retain a memory of how this tensor is used in further computations. So you can think of tensors with requires grad equals true as variables that can be changed, for example, our weights parameters in our networks, whereas tensors with requires grad equals false are constants, for example, your input data variables. Since requires grad equals true for x, then requires grad for z must also be true, since it's the result of an operation on x, which we've indicated we wish to track forward. For these reasons, its grad function attribute is automatically populated with the inverse of that forward operation, mul backward. Next, when the user specifies a backward pass during training using .backwards, the graph updates the gradients only for those for which it requires grad equals true and is leaf equals true. So here, this applies only to x, whose gradient is equal to y, since the value of z is x times y, or y times x, and the derivative of x with respect to x is 1. So you just get y. And because the value of y is initialized to 2, then the value of that derivative is 2, and the value of the gradient becomes 2. To see how this works, please go to the notebook and run through the example for this simple function L. Use the notebook to automatically calculate the output from the train rule using autograd, but for your own understanding, I strongly recommend that you also run the calculation for yourself. To verify your solution, please print out the gradient attribute of the leaf tensor x and the gradient function of the output tensor out. Next, moving on to the torch.nn module, this contains all the functions that you will need to build a neural network, including the fully connected layers, convolution and pooling operations, which we will discuss in more detail next week. Here's an example of a fully connected or linear layer using the notation from our first set of lectures in which we represented linear layers as z equals wx or wf, where w here is a weights tensor, x is an input tensor, and f would represent an activation tensor. Thus, the input to the PyTorch linear functions are just the total number of input features, which would equate to the length of the flattened input array, or the number of neurons in a previous linear layer. And the second required output, out features, is equal to the number of neurons that you have decided that you want to learn in this current layer. And note, the function always sets bias to true by default. So let's try applying this to some simulated input data, for example, by just creating a random array of size 3 by 100 by 100. So noting in the first instance that these tensors have to be cast as float, because PyTorch is only supporting gradient estimation for floating point tensors. Okay, so you have to cast your variables or your samples to type float. Then we need to flatten our array using reshape or view. Try running this for yourself. Try swapping reshape for view. Once flattened, this makes the number of input features equal to the total number of elements in our data, which is 3 times 100 by 100, which is 300,000. So this then allows us to define the first input argument for our linear function. We can then choose anything for our number of output neurons, but in this case, we've decided to choose 10. Note that you first need to define the function before you separately then run the function. And then you can run this cell and look at the output. The next thing we need to discuss is nn.functional. This module provides building block functions such as activations or interpolations and should be considered whenever you have an operation without any trainable weights. For example, the ReLU function or other activations or interpolation or average pooling. They are not, however, suitable for linear or convolutional layers which learn trainable parameters and behave differently at train and test times. For these types of operation, you must use the nn.module versions. To use nn.functional, you need to import it, for example, using import torch.nn.functional as f. Finally, for this lecture, I want to discuss dataset and data loader classes. So in deep learning, input data must be collated, pre-processed, for example, through normalization, and prepared into batches before being fed into a neural network for training. So optionally, it can be augmented or transformed in different ways to simulate the appearance of having more data than you actually do. In PyTorch, these operations are all dealt with within a bespoke dataset class. Once we have the data prepared, however, we need to feed it into the network, and this is the role of the data loader. So it supports continuous shuffling to prevent memorization, and it can schedule processing in the case that the whole dataset may be too large to hold in memory in one go. So in most cases, within this course and going forward, you will need to create your own bespoke dataset class that adapts to the properties, storage locations, and pre-processing requirements of your data. However, these classes always follow the same basic structure, starting with inheriting from the same base dataset class that's provided for you by PyTorch. So in this example, we're following an official PyTorch tutorial, which shows an example for a face landmarks dataset. So they call their dataset class face landmarks dataset, and they pass the base class so that it can inherit from it. Then what you need to do is overload the following functions: the constructor, or the init function, the length function, which returns the size of the data set or the data subset, where here I'm referencing the fact that you're going to have to create different instances of this class for each of your train, validation, and test sets. Finally, getItem is the main function that's going to pre-process and prepare your data for batching. Notice that for supervised learning, you need it to return not just a sample, but also its labels. And that when you define the class, you always define a variable IDX for indexing different samples from your data set. So going back to the constructor, this is what you call when you instantiate an instance of the class. In other words, when you create a training instance or a training data set, then this is the function that you are calling. And therefore, this is your opportunity to pass all of the variables that you need in order to pre-process those samples. For example, in this case, you pass a CSV file that contains all the data paths that tell you where to define to find your samples, combined with a root directory, so the directory where all the data is stored. And this transform object here defines the set of augmentations that you want to apply. But we'll cover this in much more detail in the Dealing with Medical Data tutorial. So outside of these basic requirements, there are no other constraints, so you're free to write the functions as you choose and perform the pre-processing suited to your problem. For example, we can write getItem such that it uses IDX to index a row of a CSV file that's been passed already to the constructor here. And we're going to use that to pull both the file path and a label. And using this, we read in the image and convert it to a float. And finally, your data is optionally transformed and augmented before outputting this processed data as a sample. Now, the option to augment is a choice. It'll occur if you pass a transform object, and it won't if you don't. This is because while you may want to augment the training data, you typically don't want to augment your validation or test data. In terms of the types of transform you might see, these augmentations can include flips, crops, or affine or nonlinear deformations, but they should make sense for your data. In other words, you should augment your data set using transforms which generate new images which remain biologically plausible in the context of your problem. For example, creating left-right flipped images of people's torsos makes little sense, as you rarely see someone's heart on the other side of their chest. Again, all of this will be covered in length during the Dealing with Medical Data lecture. Next, the data loader is an iterator which collates data into batches, shuffles input data to prevent memorization, and coordinates parallelization or pre-processing tasks through scheduling. While you are required to create bespoke data sets which overload from the base class, you'll typically just use the generic data loader and call it in the following way, telling it whether you want to shuffle and what the batch size should be. Note, for prototyping and learning, PyTorch does offer a number of popular benchmarking datasets, for example, the MNIST dataset, which represents 2D handwritten digits. To download these, you need to import the Torch Vision module, from which the list of full available datasets is searchable here. To download MNIST, for example, you need the following lines of code: importing the dataset module and the transforms module. The MNIST data constructor is then defined as follows, where you have because the IDs for train and test subsets have already been predefined, you just specify separate paths for these. And then to download, you pass the dataset constructor the argument download equals true, and to specify train equals true for the training dataset and train equals false for the test dataset. And here, the only transform that we're passing is this 2-tensor operation, which converts the image from a PIL image format into a normalized torch tensor. And then you can try out some of these dataset functions in your notebook, specifically printing out, for example, the number of examples in the train and test sets. So here we've just shown it for the train dataset where you've got 60,000 examples. And we can take one of the samples from the dataset by sampling it with ID equals 0, and this returns the first training image and its scalar label. In this case, we have an image of the number 5 with the label the integer 5, and all the MNIST images have the shape 28 by 28 by 1 because it's grayscale. I recommend trying all this in your notebook. So once we've got the data sets, then we can create separate data loaders for train and test as follows. So these each have a batch size of 128, and we're not shuffling the test data set. You can see the first argument of these data loaders is the data set objects that we just created, again, separate for train and test. We then iterate through the data set, selecting batches using the inbuilt iter or enumerate functions as shown. So here we've got an enumerate example. The difference between these is that enumerate will also return you a batch number. If you just want to visualize an example from one of your data sets, then you can instead use this syntax using this next function. We can use this, for example, to check the batch shape as shown. And finally, just looking quickly at the documentation for toTensor, this converts a PIL image or a NumPy array of shape h by w by c with values ranging from 0 to 255 to a torch float tensor of shape c by h by w with normalized values in the range 0 to 1. As we will show in the notebook, the reordering of dimensions is necessary in order to present the PyTorch networks with tensors in the right format, and we will try this out in the tutorial. So that's it for PyTorch Basics. In summary, PyTorch is an easy to use and flexible deep learning coding framework which is designed to be very similar to Python. It's therefore interpretable, capable of running line by line, which makes debugging easier, and it achieves this through building computational graphs dynamically, line by line. And it achieves this through building computational graphs dynamically, refreshing these at every new iteration through the forward pass. PyTorch computational graphs are constructed using its AutoGrad class, using the fact that PyTorch tensors not only store data, but also the gradient functions and the gradients themselves. PyTorch has several different classes or modules for building and training your networks. Of these, the torch.nn contains the major building blocks that you'll need for building your networks, for example, linear and convolutional layers, as well as pooling and batch norm functions, all of which we will cover in the next few weeks. On the other hand, torch.nn.functional is defining functions, is what you should use to define functions with no trainable parameters, for example, activation layers. So torch.nn and torch.nn.functional are therefore they're providing you the baseline structure from which you can write your network classes, which we will talk about in the next lecture. Finally, prior to training anything, you need to pre-process and batch up your data. So this is done with dataset and data loader classes. As we said, typically you don't need to do anything to the default data loader class, you just use it. On the other hand, while PyTorch does offer access to some common open data sets, in general you're going to need to define your own bespoke dataset class for your own bespoke data sets, and these overload the base dataset functions to support loading and pre-processing of your data. Thanks for listening, and in the next lecture we're going to start to cover how to create PyTorch network classes.